Hello and welcome to Triple Index Storage. My name is John Snelson and I'm Principal Engineer and Lead of the Optic Engine team at MarkLogic. This is part 4 of a 5-part deep dive into the Optic Engine. And in parts 4 and 5 we're dealing with how the triple index works and mostly with things that happen on the D node in MarkLogic. If you're interested in other parts of the Optic Engine, including the E node engine and optimization, you may want to go and have a look at parts 1 and 2. Now, just by way of introduction, MarkLogic is a document database, and that means that everything that's stored in MarkLogic starts as a document. And the triple index is an index because the triples live in the document and they're taken out of the document and put into the index, whether that's by using our triple format or by using TDE to extract those triples from the document. So when we store triples in MarkLogic, triples are a subject, a predicate, and an object. And those triples describe the edges of a graph, where the nodes in the graph are the subjects and the objects, and they link together by using the same subject or by using the same object. But we also store our tables in the triple index as well. That may be slightly confusing to start with because it's called the triple index, but this is how we do that. For each cell in your table, we store a row ID, a column ID, and then the value from that cell. And in that way, the cells of the table look like triples and are stored in the triple index. Now, one other thing to understand before we really get into talking about the triple index storage is the idea of integer compression. And this actually underpins a lot of the compression that we do in the triple index. The idea is that for smaller integers, we'll store them in a format that takes fewer bits. So the number 0 takes 1 bit. The number 1 takes only 6 bits. Actually, 10 also takes 6 bits. And you can see in this table 100 takes 11 bits. And the number of bits used increases as the integer gets bigger. So we're going to be doing a lot of things in the triple index to try and use smaller integers so that we get a smaller size on disk. We get compressed storage. So you may have seen slides like this. Indeed, I have shown slides like this to kind of illustrate how the triple index looks. Lies. I'm afraid it isn't like this. But what I'm going to do is delve deeper into and get more and more accurate in what it does actually look like. In this case, this slide is designed to illustrate that not only are we storing triples in the triple index, the subject, predicate and object, but we're also storing the fragment ID of the document that it came from, and potentially also even start position and end position, because all indexes in MarkLogic support storing positions. Usually the triple index positions aren't turned on, and to be honest, I don't think I've seen many people using them, but that facility is there. So slightly closer to the truth, deeper into the abstraction. One thing to note is that we don't actually store the values in the index. We store a value ID and the values are stored separately. That's called dictionary compression, where the values are taken out and stored once and their ID is used instead. Another thing to understand about the triple index is that we store each triple 4 times, in effect. 4 times under different permutations or sort orders. So you can see the list of permutations there in the bottom left. So for instance, SOP permutation stores the subject S as value 1, the object O as value 2 and the predicate P as value 3. And the triple index is sorted according to first value 1, then the permutation, and then value 2, and then value 3, etc. Actually, we sort on all of those columns from left to right. So what that means is that we get to have different sort orders in the triple index. We can return results in different orders, and we can look index entries up by different parts of the triple. But there's more. We also store type IDs in there as well. Now what we actually store in the triple values is as much information as we need in order to sort those values. But believe it or not, there's some information in values that isn't used for sorting. An example of this is time zones for timestamps and date time values. Once we've normalized those date time values, we don't need the time zone in order to sort them. But people expect to see the same time zone coming back out of the index as they put in, and so we store time zone information in what we call the type ID. Other examples of these, and this makes more sense of the name, other examples of these are the actual specific derived schema type for that value. So it may be a my hat size, but my hat size may be derived from an integer. So we'll store an integer, and we'll store in the type information, we'll store that it's actually a my hat size value. Recently we've added element level security support into the triple index, and that actually added a new column at the very start of the sort order to store the role set key. Now that role set key represents all of the roles necessary for a user to be able to see the information in that given section of the triple index. And we were able to add this in a backwards compatible way because there was no privileged information in the triple index before we added this support, and therefore it was as if every triple index entry in the triple index had a role set key of 0. But now that we support element level security, that role set key can be other numbers and can have secure regions that only certain users are allowed to view. So let's again take a look at what it means for these columns to be stored in a certain sort order according to the permutation here. So if we have two role set keys, as can be seen in the table at the bottom here, two role set keys to look up, then we're going to be able to identify two regions of the triple index that we can read. So rather than reading the whole triple index, there are two bigger regions corresponding to each of those role set keys that we can read from the triple index to get the information that we need. That's because that's the first sort order, so everything for that role set key is held together in a contiguous region of the triple index. So then for value 1, the second sort order, there are regions inside that role set key region that correspond to that value. So we could use a role set key, a fixed role set key, and get back things in the order of value 1. But if we have a fixed role set key and value 1, then the information we read back is now in the order of the permutation. Now if we fix that again, in this case to PSO, then we're talking about even smaller regions. We've targeted our triple index read even more, and we're getting things back in order of value 2. For this permutation, value 2 here is the subject because it's PSO. So that would be subject order. And again, if subject is fixed, that defines an even smaller region of the triple index for us to read. So we can be more and more efficient the more of the major sort orders we have as fixed values. And then that means also, though, that the minor sort orders can be returned and the data will be in that order. So, if this was some information in the triple index, there's some things to note here. So we got some repeating values in this data. There's roll set key is repeated twice. So we can actually write that as two lots of the zero roll set key. That's called run length compression. And we do that on the four top sort orders here, the four top columns. So for value 1, we've got two lots of value 1 ID 3. We've got two lots of the permutation PSO. That's actually recorded as a 0. That's the number for that enumeration. With value 2, those values are different, 4 and 5. So we just got one lot of ID 4. And then after that, we don't run length compress, mostly because we're not expecting a great deal of repeats of triples that are the same, that have the same SP and O. And so value 3, we don't run length compress. The rest of that data is just put into the triple index without run length compression. What that means is because we've recorded two lots of roll set key 0, the next row doesn't need to record a roll set key. Neither does it need to record a value 1 or permutation. So we can start directly with the value 2 ID. So one lot of value 2 equals 5, and then the rest of that information. The run length compression saves us quite a lot of repeated information in the triple index. Actually, for this reason, some people query the way that we store tables, and they say, well, you're repeating the row ID over and over and the column ID over and over in the triple index. Doesn't that waste space? And the answer is no, not really, because of the run length compression. We store the row ID once, and if every triple has got that row ID, we just say, 500 lots of that row ID, and we don't have to store it again. So no, it doesn't take up space in the triple index particularly. It's actually pretty space efficient. Another thing to look at is remember that we like small integers. We aim to put small integers into the triple index. Now we have got two value IDs that follow on from each other, value IDs in value 2 column. We've got 4 and 5. They're quite close to each other, but they could be quite large numbers. Here we've got the start position and the end position. Now the position number could be quite large, but we expect the start position and the end position for any given piece of information in the triple index to be fairly close to each other. And not related necessarily, but also there's a lot of entries in the triple index that don't have any type ID information. They would be storing 0, 0, 0. So maybe we can compress that better. So difference compression works like this. Instead of storing 4 and then storing 5, we store the difference between the two. So we store 4 and then we say add 1 to the previous number, which was 4. And we can do that because they're in sorted order, and therefore the numbers are likely to be close to each other. The difference is likely to be small. We like small integers. They compress down to much fewer bits, so that is a big win for us. When we have the start position and the end position, we don't store the end position, we just store what we need to add to the start position in order to get the end position. And if we've got 3 zeros under the type IDs, actually we just store a Boolean bit, 0 or 1, as to whether there are type IDs. So in this case we can store 1 bit, there are no type IDs, and we save the space for those type IDs. Now what we've created here is a triple index which is really nicely compressed, but each triple depends on the values in the previous triple, both for the run length information where the roll set key and value 1 are carried forwards, for instance, and for the prefix where we need to add something to the previous ID to get the new ID. So we can't now jump into the middle of that information and start reading, because we won't know what has come before. The way that we solve this in the triple index is we store blocks of 4K of information. So the prefix compression and the difference compression starts anew at the start of that 4K block. And that gives us intervals between blocks where we can jump in and start reading the triple index. So that's what helps us to be efficient when we're reading the triple index. We choose to read the fewest number of blocks in order to answer the query. Now, in order to know what information is in those blocks, we actually have an index file to the index. So these are actually the names of the files on disk at the side here on the left hand side. Triple data contains the blocks, and triple index contains information telling us what those blocks have in them. So we store we look at the first triple in that block, and we store information about it in the index. We store its roll set key, first value ID, permutation, and second value ID in that index. So we can jump to the exact block where we're first likely to find out information about, for instance, a given roll set key and first value ID. We can use the triple index to do that. Now, when we store values, you could see the values as being something like a table here, where we've got the type or the tag for that value, and then we've got the actual tag specific data for that. So there's IRIs here. Notice that the IRIs are quite long strings, and there's a lot of repeated information in there. There's integers. The integers could be quite big, actually, but we know that they're in sorted order. And again, we might want to maybe do some difference compression there. And row IDs. Actually, row IDs consist of two values. The first is a value that identifies the table or view they come from, and the second is something that identifies the row. So that first number is repeated over and over. So we do prefix and difference compression on the values that are stored in the triple index as well. In this case, we're storing a tag plus 1 to indicate that there's an entire value uncompressed, and then we're storing a 0 to say, well, this is a prefix or difference compression from the previous value. When we do strings, we use prefix compression. What that means is we first store a number. In this case, the second row here has 25. That means take 25 characters from the start of the previous string and then add on this next string. So in that case, when we have IRIs with a lot of repeated prefixes, we don't store that prefix over and over. We can compress those strings. With integers, we're storing the difference. So where we see 33 here, that means add 33 to the previous value of 67. And with the row IDs, again, we also store difference compressed first values, table IDs. So that a simple 0 means that this is the same table as the previous entry. So because we're using prefix and difference compression in the values, again, we have the same problem that we have to start reading from the beginning before we can, and work our way through all the data before we can find a specific value. So again, we split these up into blocks. The triple value data contains those blocks, and triple value index contains a list of the first value in each block. Because we store values in sorted order, and we assign therefore IDs to those values in sorted order, sorting by value ID is equivalent to sorting by value. And that's a really useful property for us. It means that we don't have to cross-reference the values just to be able to search through the triple data. It also means that value ID order is the same as value order, and so the triple value index stores the first value ID in that block, and we can look values up by ID, and we can look values up by their actual value using the same structure, the same sorted index. Now you'll notice that there may be a problem with large strings here. We're storing 4K blocks, and if the string information does not fit in that 4K block, that's going to cause us an issue. In fact, if a string is bigger than half of a block, so 2K, then we don't store it in the block at all. We store it outside of the block. And where we store that is in the StringData and the AtomData. Now these two files are shared in common with all string range indexes as well. So all string range index data is stored in these files. And what happens is that the string is atomized into tokens or atoms, and each atom is assigned an ID and stored in the AtomData. And that ID is assigned based on frequency of occurrence. So the most often used atom, which is often something like space, for instance, that gets the lowest ID. Again, we're after storing smaller IDs, smaller integers more frequently. And then we have the string data, and that's a list of atoms, a list of atom IDs that need to become concatenated together to recreate that original string. So obviously doing that takes time. So larger strings, they can be stored and compressed well, actually, because each atom is only stored once, but they take some time to put back together, and so it takes a while to retrieve those from the triple index. In addition, the string data and atom data need to all be brought into, well, actually all the string data, all the atom data needs to be brought into memory during a merge, because we assign those IDs based on frequency of usage. And we won't know frequency of usage until we've brought all that data into memory. So during a merge, we like to keep the amount of memory used down during a merge so that you can merge large files. But if there's too much information in the string data and the atom data, then it's not possible to merge large stands anymore. And that can be an issue. So the conclusion of this is that whilst it's possible to store large strings in the triple index, it might not be the best idea, and they're probably better off kept in your document data rather than being put into the triple index. Now, where we have blocks in the triple index data and the triple value data, that gives us an opportunity to add some header information to those blocks, and that's what we do. The most important information that there is in that header is probably the checksum. And what happens is when we read a block from disk, we calculate a checksum on it and we compare that to the checksum in the header. And if those values are different, then the block that we read is different from the one that we saved to disk. Now, what that means is if you see a triple index checksum error come back, it usually doesn't mean that there's a problem with the triple index or with MarkLogic. It most often actually indicates that there might be something wrong with your hardware, with the disk that it's running on. It's good to be able to have that kind of verification in there to make sure that what we read from disk is coming back the same as we wrote it. But it does potentially indicate hardware problems or deeper problems than something that's in MarkLogic. Other things we have in the header information are things like version number, count of values, the starting value ID, and things like that. They're all useful for being able to read the data back, and also the version ID helps us to change the triple index and add new things, like for instance the new role set key that we added for element level security. We can add that in a way that does not need an upgrade, a bulk upgrade, and does not affect users, because we just change the version number and we are able to read both version blocks from the triple index. So in conclusion, what we've learned today is that there are both triples and triple values, and hopefully you have a better understanding about what those do. We've learned about the triple index permutations and the way that they affect the sort orders and the access to data in the triple index. We've looked at various ways that the triple index is compressed and the fact that it has a block structure. And these are all foundations for understanding the efficiency of triple index queries. So do look up part 5 of this Optic Engine deep dive, where we discuss how triple index queries are executed, what we can do efficiently, and how potentially that can affect the way that you write queries. Thank you very much for your time.